of years exploring those continents to learn what was actually there, what the continents were like. In the same way, in extrasolar planets, we have seen planets, we know that they're there, but we don't know anything about them. And I still think we have dozens or hundreds of years of exploration ahead of us to figure out what they're like. And so what I want to tell you about today is just mostly what we've seen so far, just the outline, and it will leave to your imaginations when you go home tonight to think about what the details are, what the planets are actually like. So planets come in different sizes. You guys probably knew this already. So Jupiter and Saturn are gas giants. Jupiter is about 300 times the mass of the Earth, and it's mostly hydrogen and helium. Uranus and Neptune are about 15 times the mass of the Earth, so much larger than Earth. We've got Earth, Venus, Mars, Mercury, no Pluto, properly classified as a fourth planet. Planets come in different sizes, right? But all sizes of planets are incredibly small. So to scale, this is the size of the Sun, and we've got Jupiter, Saturn, and there's the Earth right there. So planets are tremendously smaller than their parent stars. 1 million Earths could fit inside the Sun. 1,000 Jupiters could fit inside the Sun. So one of the problems about trying to find and understand planets is that they're tremendously smaller than stars are. Also, stars are bright. You can look outside in the morning and see the sun coming up, and you can tell stars are bright, right? Stars are much brighter than planets too. A planet like the Earth is about 1 billion to 10 billion times dimmer than the sun. So if you want to try to find a planet like the Earth around another star, you have to be able to see something that's 10 billion times dimmer than the really bright thing right next to it. And that's an amazing technological challenge. This is the state of the art now. This is a really bright, young, hot super Jupiter that's only 100,000 times dimmer than its parent star. Those are the kinds of planets we can take pictures of today. If you want to take a picture of an Earth, which wouldn't actually be a picture, it'd be a dot, you want something that's another 100,000 times fainter. And that's something that we just can't do today, and we won't be able to do that for probably another few decades. But there's another method we can use that uses the star's light to our advantage. If you're trying to take a picture of a planet, the star's light is really your disadvantage. But we can devise methods that use the brightness of stars to our advantage. And that's what I want to talk to you about today, is eclipses of planets in front of their parent stars. Those are called transits. And if we can look at the brightness of the parent star, we can actually find planets that way. Okay, so this is called the transit method. So you want to look at the brightness of the star as a function of time. And so when the planet passes in front of the parent star, it blocks out a small amount of the parent star's light. This is just like an eclipse to some degree that we see for the moon going in front of the sun. And so a Jupiter-sized planet would block out about 1% of its parent star's light. An Earth-sized planet is 10 times smaller in radius, so 100 times smaller in cross-sectional area. So an Earth-sized planet will only block out 1 part in 10,000 of the parent star's light. So you really have to be able to see tiny changes in the brightness of the star if you want to see a planet this way. But that's something you can actually do. It is possible to build detectors that can see that tiny change in brightness. And so the nice thing about transits is that you can figure out how big your planet is. A small planet would block out a tiny amount of light. A bigger planet would block out a larger amount of light. So it's pretty easy to measure the size of your planet, which would maybe tell you what it's made of. If it's mostly a rocky planet or a hydrogen planet, because we talked about how Jupiter was much bigger than the Earth. And you can also, if you see the transits happening over and over again, you can measure the orbital period of the planet. If you see a transit every 10 days, you then know the planet's in a 10-day orbit. And you can actually use Kepler's laws to figure out how far that planet is from its parent star. So just from simple geometry, you can see the planet pass in front of its star, and by watching it happen over and over and over again, you can figure out how far that planet is from its parent star. So you can learn a fair amount just by staring at stars and measuring them dimming from time to time. So transits happen in our solar system as well. So we're at Earth, we're the third planet from the sun. So we can see Mercury and Venus pass pass in front of the sun from time to time. Those are called transits. And so Kepler, the very nice beard and mustache over the upper left, I think astronomers today should really take a cue from him and really expand our facial hair. So Kepler was in the 1600s, and he devised some laws of motion. He was the first person to predict that from Earth we should be able to see Mercury and Venus occasionally pass directly in front of the sun. That's called a transit. And so he predicted this would happen in 1639, and then there's a gentleman named Crabtree who was the first person to see a planet pass directly in front of the sun. So, and that's how you can actually figure out the size of Venus. This is a very beautiful painting of him and his wife and his young children standing by, as you can see Venus passing right in front of the sun there. And so there's me and my son Finn on campus in 2012 looking through a special telescope to look at Venus passing in front of the sun. I would love to know what happened to that hat, but I lost it. But maybe I'll get a similar hat someday. But if you want to see the next transit of Venus, eat your vitamins because it's going to be in the year 2117. They happen about every 100 years. There'll be 2 8 years apart. So there was one in 2004, 2012. Next one's 2117, then 2125. So if you really want to hang on to see that one, you really have to want it. So this is my favorite picture of the 2004 Venus transit. This is the sunrise off of the eastern coast of Florida. You can see some fishermen, you can see a pelican, and you can see Venus. And that's probably my favorite picture in astronomy that I've seen in the last decade or so. This is not the same thing. This is the moon passing between the Earth and the sun. This is the moon shadow falling on the Earth. This is a total eclipse, so if you were right in there, you would of course see the moon shadow blocking out the sun. So on Earth, we're very used to objects passing in front of the sun, blocking out the star's light, be it the moon or be it Venus. These are things we've seen for hundreds of years. Or for eclipses, much beyond that in the past. And so the idea was that we could try to use this method to look for planets around other stars as well. And so there's a gentleman named Bill Barucki, who's a scientist at NASA Ames Research Center. In the 1980s, he had this idea of maybe we could build a space telescope that could stare at a huge number of stars for many years. And that space telescope could just do one thing, but do it really well. It could look at maybe 100,000 stars for many years and just look for these periodic dimmings. And that was the whole point of the telescope. Something like the Hubble Space Telescope looks in the ultraviolet, the infrared, it can take spectra, it can take pictures. That's Hubble. The Kepler telescope doesn't do any of those things. All it does is it looks at one patch of the sky for 4 years, and all it does is monitor the brightness of 100,000 stars. It's really a combination of a really, really boring thing, but with really exciting returns. And all it does is monitor the brightness of stars. And so what you might imagine is that if you looked at 10 stars trying to find planets, and you didn't see any, it doesn't really tell you much because it's only 10, right? But if you looked at 100,000 stars, and you didn't see any planets, that would tell you something extremely important. That would tell you essentially that planets don't exist. If you had a sample size of 10, you really couldn't be confident in your conclusion. So that's really the power of statistics, why you want to look at so many stars. So if you found thousands of planets, or hundreds of thousands of planets, that would tell you how common they are. Of course, one of the things I should tell you for transits, right, is that we need to see those planets almost exactly edge on, right? If there's stars that have planets, but if we're not seeing that system exactly edge on, we won't see the planets pass directly in front of the parent star, right? So we need the geometry to be right. So that's another reason why you want to look at so many stars, is because the stars are just randomly thrown throughout the sky, so lots of stars will have planets. But the planets, as we see it from Earth, won't pass directly in front of the star. So we need a really big sample size. And so the Kepler field of view, the Kepler was essentially a 100 megapixel space camera built to stare this is the Milky Way galaxy, and it stared just outside of Cygnus looking at 100,000 stars. And so it kind of looked backwards along the Orion arm that we're in here. It looked backwards, and it mostly looked at stars. In this picture, the stars look pretty close by. But really, in general, the stars are pretty faint. They're pretty far away. So none of these planets are ones that we could visit. They're far away. They're typically kind of like 1,000 light years away. That's kind of the average Kepler star, and we're looking back over there. And so what Kepler was designed to do was actually find planets that were potentially like Earth. So Earth is in a 1-year orbit around a star that's about 6,000 degrees. And so we know on Earth we have a certain temperature that allows us to have liquid water on our surface. Whereas Mars is a little bit too cold, Venus is a little bit too hot. And so there's a particular region called the habitable zone. The habitable zone is a region where we think planets can have liquid water on their surface. And so if we want to find life as we know it, there's also possible to have life as we don't know it, of course. If we want to find life as we know it, we would like to find planets where we think they could have liquid water. And so if you're around a really bright, hotter star, you'd want to be further away. If you're around a dim, faint star, you'd want to be closer in. This region's called the habitable zone. And so Earth, remember, Earth goes around once per year. And so if you want to see transits of Earth-type planets, you want to be able to stare at those stars for multiple years, because an Earth-like orbit would only go around once per year. You want to see that happen several times in a row. So that's why Kepler was built to stare in one patch of the sky for 3 or 4 years, because you'd want to see 1-year orbits repeat, basically. These orbits, like the Earth, are 1 year. These closer in orbits are shorter. These further out orbits take longer, but really you want to stare in one patch of the sky for a long period of time to see these transits happen over and over again. That was the whole point of Kepler. This is what Kepler looks like. There's a person kneeling down to scale. It's a 1-meter telescope. These are about 3 feet. And the solar panels on the side. And it was really built to look for planets around the size of the Earth, maybe 3/4 to 1.5 times the size of the Earth, in this habitable zone, a region around other stars where we think planets might be temperate enough to have liquid water. And it monitored about, I said 100,000, it was actually about 150,000 stars for about 4 years. And so one of the things this is the Transamerica Pyramid in San Francisco. You might be wondering why I put this up here. Kepler was built to see parent stars that would dim by about 1 part in 10,000, or even less than that. Right? I mentioned when Earth passes in front of our sun, it only blocks out 1 part in 10,000 of our sun's light. And so that's like, if you imagine all the lights lit up in every room in the Transamerica Pyramid, and you imagine there's a shade on one window in that pyramid, and someone pulls that shade down by 1 foot. That's the scale, if you imagine. So you imagine all the windows lit up, and somebody pulls the shade down by 1 foot in one window in that building. That's the scale that we need to see these dimming events. And so the Kepler mission was built to be able to see these tiny dimming events for the parent stars. Sure.
So of the 100,000 stars you're looking at, what's the probability of finding a star with its orbital plane parallel to our view again? So the 100,000 stars, what percent can you actually see transits?
Okay, the question was, since we need to see edge-on planetary systems to see transits, what's the likelihood of actually seeing an edge-on system such that we can see a transiting planet? And that depends on how far the planet is from its parent star. It essentially goes as the radius of the star divided by the orbital separation. So if the planet's orbit is at 10 stellar radii, which is really close in, then the transit probability would be a 10th. If you're at 100 stellar radii, it's 100th. And so the vast majority of systems, we won't be seeing planets because we won't be seeing that precise alignment, which is another reason why you'd want to look for 150,000 stars.
I was just curious, of the 150,000, how many stars are showing?
I'll get to that. I'll get to that. Yeah, sure.
I thought you paid me to come in here and ask that.
All right. So what Kepler sees is not super exciting to some degree. You measure the amount of light from the star as a function of time in hours, and you see a constant brightness, and the planet blocks out some of the parent star, and then it goes back, and then it comes around again. And so from that, you can measure the size of the planet, though. You can measure how big it is. Let's say this planet's called Kepler-10. It's 1.4 Earth radii. So what Kepler returns is data that looks like this: brightness versus time. So we really don't know anything about the planets other than their size and how far they are from their parent star. And from that, you can maybe make an estimate of how hot they are as well. Okay, so this is a view of planets versus time, 1996, 97, 98, 99. I'm going to start it over again. Okay, this is size of the planet relative to Earth: 1 Earth radii, 4 Earth radii, 10 Earth radii, orbital period in days. So Earth is at 365 days. This is Earth size, Neptune size, Jupiter size, 2004. 2005, 2006. These are all planets found before Kepler, all before Kepler. So Kepler launched in 2009. I was down in Florida to see the launch. It was a really cool night launch. And so at the time, there were a couple hundred planets detected by various methods. So transits are this dimming events. So that it predominantly found close-in planets, and that's because the planet's very close in. It's much more likely to block out its parent star's light to transit. There's other ways of finding planets. Another common way is called this Doppler method, where if you see the parent star wobble towards and away from you, you can see the parent star's light Doppler shift. Just like if a train comes by, you can hear the train whistle Doppler shift. So that's another common way of finding planets. So 2009 is when Kepler launched. Oh, we're starting over. Okay. All right, so I'll describe it again. People first started finding exoplanets in 1989 and then 1995. When I was a grad student, I started in grad school in 1999, and there was just a handful of planets, and people found more as time went on. So the planets that are going to be coming in from Kepler after 1999 are going to be in yellow. Oh, after 2009, yeah. 2009, 10, 11, 12, 13, and that's a Kepler planet. Okay. So there were about 400, 500 planets known before Kepler. Kepler's added at current tally, about 3,500. And so it's been a stunning increase in the number of planets. And so what the other methods were predominantly much better at finding giant planets. So what people had mostly found were mostly giant planets. But Kepler was sensitive enough to find much smaller planets. And what Kepler has shown us in a very dramatic way is that smaller planets are much more abundant than larger planets. In our own solar system, it's not really clear that you would know that. We have 4 giant planets, we have 4 rocky planets. You might think that maybe they're similar in number. What Kepler has shown us, at least close to the parent star, that small planets are dramatically more abundant than large planets. So these are objects that are 1 Earth radii, 2 Earth radii. These objects in here, people call them super Earths.